So for my part, I won't talk so much about Annex 1. I won't talk so much about USP 665. What I would like to present you today is really how, in fact, extractables are generated. And besides the generation of extractable, what are the other modifications we can expect on polymer, on plastic, following the radiation sterilization or following the irradiation. So let's start on that. So you might know by heart, of course, the different steps you can have either in the upstream or in the downstream. I don't want to describe everything. That's not the purpose at all of my talk today. What I would like to emphasize that most of the time when we are dealing with single use in the different part of this biopharmaceuticals manufacturing, we deal with sterile and integral single-use system. And what I would like to emphasize today, what could be the impact of the sterilization at the end, to achieve the sterility. That's really my focus for my today's presentation. So what you may know. You may know by heart, at least I keep saying that everywhere worldwide, that at the end the sterilization could be achieved either by using gamma rays, X-ray, and E-beam. The purpose of sterilization using different radiation technologies is always the same, killing the microorganism, but the effect of using ionizing radiation definitively to disrupt any biological event in the microorganisms, leading to their death. That's the goal, universal goal. And for that, there is no doubt. You have to keep in mind as well, that whatever the radiation technology we be using, a dose is a dose. Typically in the pharma industry, we use the VDMAX approach with a minimum dose to target of 25 kilograms. This minimum dose must be achieved either with using gamma ray, X-ray, or even E-beam. That is to say, all the requirements of the famous sterilization standard ISO 11137 are the same. The requirements are the same. The purpose of the sterilization stage, of course, is to achieve the sterility, and all the sterility claims must be achieved with all the technologies in that field. You might know as well that definitively this ISO standard focuses a lot about all the microbiology aspect. It just says, from the material of construction aspect, please qualify at the worst case dose. Nothing else. What does it mean, worst case dose? Worst case dose for all the polymer, I will show you, is not at all the same. We could be talking about 50 kilograms for one polymer, but as a worst case dose, but we should be talking about 10,000 kilograms for another polymer. So here, let's stick to the pharma house application we are focusing on and see how we can deal with that. Okay, so when we would like to understand what could be the impact at the end of the different sterilization stages, you need to understand, of course, the key knowledges defined and the key requirement defined by the ISO standard 11137. You need to understand as well what is the influence of the radiation physics. That is to say, how the gamma rays and X-ray will interact with the material of construction used in our single-use system. You need as well to understand what are the modifications induced by the interaction between gamma and X-rays. Finally, you need to understand what are the different testing recommendations. It could be PSA, it could be biopharm, it could be USP, it could be many other guidelines or standards you can find into the market. And of course, at the end, you need to know the application. I emphasize as well in right part of my slide that, as you can see, you need to take several parameters in account to be able to do so. Of course, like Sartorius, like Sativa, like the other today, were integrated single-use system. Definitively, we purchase some component from other suppliers, and of course, to be delivered to the biomanufacturer. But to be perfectly understand as well what could be the impact, we need to talk as well with sterilization contract sterilizer. It is really important because they will be given the right dose to our product at the end with our specification, of course. So that's why communication is key every time. So what I would like to describe today quickly, I won't dive too much into the details, don't worry about that, is how we were able to define an holistic three-level approaches to be able to understand what could be the impact at the method of construction, at the product level, component level, at the end of the sterilization stage. So you might be aware that, for instance, BPSA published in 2021 an X-ray implementation guideline based on the quality text matrix published as well by the BPSA in 2015 to be able to dive into this three level of testing. We also published with Team Nablo. So briefly, the Team Nablo is a consortium between different industries and companies like Sartorius, Cytiva, Stryker, Becton Dickinson, and so forth, as well with different universities either in France or in the USA, to be able at the end to understand, not only to show, but to understand what's going on when there is a sterilization while using ionizing irradiation. So I gave you all the two references, and you can, if you would like to dive in all the details, and please come back to me if you would like to know more. And of course, one of the first things we need to understand, and it is the key part of that, it is what could be the impact at the product level. Of course, everyone will be using not only the material construction, not only the component, but will be using the product. But to be able to assess the impact of the level, we need to understand what could be the impact at the component level, at the material construction level. And to be able to understand that, we need to check what are all the mechanisms of this degradation or modification at the plastic level, at the chains level. And I would like to dive quickly to show some example what has been done. Otherwise, I would need maybe 2 or 3 hours to show you everything. That's not the purpose for my today talk. Okay. One of the first questions, of course, before diving into the impact, do we know that if all the plastic material will have exactly the same, will submit, will withdraw the same modification upon the sterilization using ionizing irradiation? You might know that the answer is no, definitively no. The material compatibility, the polymer compatibility for ionizing irradiation is not the same. It is definitively based on their chemical structure. Basically, you can find 3 families of polymer upon, I would say, irradiation compatibility. The one who could be cross-linked, the one who could be degraded, and the one they don't care at all. Basically. For that, we could have as well some general recommendations. So the CERN first published in 1988 a first report. What we can do in terms of material selection. It has been made for the nuclear plant, so long time as well. And now for the pharma and medical device industry, we need to refer to the METIR 17. Sorry, there is a typo, 17. There is no O in between. Definitively, it is really a guideline to allow you, I would say, defining and making the right selection to select the appropriate material for sterilization using ionizing irradiation. We cannot start from scratch in 2024, not anymore. That's not possible. So if we look now, what do we mean by cross-linking polymers, for instance? Polyethylene, I think it is one of the most used polymer in our industry to produce single-use system. It is cross-linked. Is it a problem to see some cross-linking? It could be not. We will see that after. So it is well known, for instance, that compared to what all the rumors are, HDPE are more impacted than LDPE, which are more impacted than LDPE. It's a fact. So I will show you some examples, for instance, in one of film, the S80 film, as you can see the structure over there, PE, EVOH, PE, and I will show you some example of a medication this structure can withstand after the radiation. After that, I said there are polymers that don't care at all about irradiation. As soon as you have an aromatic structure, for instance, a PET, PSU, PC, they don't care. We can go up to 10,000 kilograms without any structural modification on that. No problem. So it's very convenient. Maybe you can see some discoloration, but there is no change at all after in the structure. So that means no loss, I would say, into the tensile strength, so no loss of the mechanical properties and so forth. And the other side, we have the polymer where we could pay attention to. That's the polymer which cannot withstand so well to irradiation. I would like to give you two examples. For instance, everybody knows the PTFE. The PTFE is perfectly the material which does not withstand at all irradiation up to 50 kilograms. So if someone would like to select, yes, but you have to be careful that definitively the PTFE will become brighter at 50 kilograms. The other polymer I would like to give you as an example is a POM. The POM at 30 kilograms start becoming brighter and like dust. You can touch it, break it without any problem. Full stop. And you might see, okay, polypropylene is in that range as well. But in your mind, okay, oh my God, I use a lot of polypropylene in my single-use system. What could be the risk? Don't worry. That means that the polypropylene is additivated, is made with a lot of additive, with a lot of antioxidant to be sure that at the end they can withstand the radiation up to 50 kilograms. Don't expect to see a propylene used in the pharma industry to withstand up to 100 kilograms, like we can do with a polyethylene. So that means before doing any extractable study, you need to select the appropriate polymer to withstand sterilization while using ionizing irradiation. Polyethylene is better. HDP is definitively better than using PP. But it's up to you at the end. Okay. Now, finally, why do we have some modification in the polymer? With autoclaving, we saw nothing. Why using ionizing irradiation, we could see something? I called that the seed of modification. What are the seeds of the modification? What are the root cause of all the modification we could be induced by using ionizing radiation for the sterilization purpose? You might know, I would dive a little bit, just a little bit into the physics in that case. You might know that as soon as we have ionizing radiation, either gamma or X-ray, they will interact with the matter. The purpose, of course, is, as we say, is to depose those to achieve the sterilization at the end. By deposing those, we mean that the gamma rays or the X-ray will kick out one electron here, and it will be lost somewhere in the bunker. We don't care. But what is important, as soon as the secondary electron is kicked out of this shell here, they will interact deeply with everything around and what we call depositing the dose. But that means as soon as we have an electron removed from one atom here, it would create, I would say, hole. And it is what we call a free radical. And as you may know, radicals are extremely reactive. You may compare, if you, for instance, you would go to the chemical dance floor with a radical, it's like a single. They would like to bind to everybody, randomly, blindly, I would say without any doubt. Sometimes it could be good, sometimes not. But that's the life, that's the fate of the radical. They would like to bind, not to stay alone. So that means at the end, radicals are extremely reactive. And there is a way to track the radical using electron spin resonance. So if we are able to understand the fate of the radical, we might be able to understand what are the main root causes of the modification induced in our polymer, used in that single-use world. And it is what we will do. So I would like to give you one example, as I said, on the 80 theme of different ESR monitoring we have done. So I don't expect you to understand the graph, but it's just a signal of the ESR we have obtained. But easily, what you can see is that all of the scenarios have the same shape. It is important. And all of the signal, close, I'm too small, but right here, in the center. It means very important thing. That means that the nature of the radical is the same. Because it crosses exactly the same position and because the shape of the signal is the same, it means that the nature is the same, whatever the radiation technology we have used. I repeat once again, it is the same, whatever the radiation technology which has been used. Secondly, another graph to show you what is the lifetime, for instance, typically on this kind of radicals. So here we plotted the concentration decreased over time after gamma radiation with 2 doses, X-ray radiation with 2 doses, and E-beam radiation with 2 doses. What you can see is that there is exactly the same decay, exactly the same lifetime. So what we can see that by using ESR, we are able to say that the nature of the radical is the same, whatever the radiation technology, and even though the dose is not the same. So sometimes it could be 25 kilograms, sometimes it could be 50 kilograms, sometimes it could be 100 kilograms. We don't care. The nature is the same. So concentration is not the same as expected. For those we want, we publish many papers on that. I'll just give you 2 examples on that field, and if you have some questions, come back to me as usual. Okay, now just another example, what is a radical? In fact, the radical, as I said, is something we can be cut either by the VOH in the case of the ACT or by the polyethylene. Now we need to understand what could be the impact of such a creation. What could be the fate of this radical at the end? And we need to know what could be the modification induced by the presence of these radicals. Okay, so now the radical can react definitively with the polymer, as I said, but they can react as well with the antioxidant. If they react with the polymer, definitively they can provoke a cascade of reaction, leading at the end to either a chain scission, chain branching, or a cross-linking. The chain scission we cut, cross-linking we linked. And we can also create a cascade of reaction with many antioxidants. That's the purpose of the antioxidant, to be in the polymer, to be sure they can protect the polymers, either for the transformation from the pellet to film, or to any component, or to the sterilization purpose. And of course, the purpose of everything I would like to show in the next couple of slides is just to check, okay, with the same radical, can we expect the same modification? And all the different levels of check. So finally, what could be the modification? If we assimilate, for instance, a polymer, a plastic, it's like this spaghetti plate. It's just an entanglement of different chains. And to make it more lubricant, you can add some tomato sauce. And the question, what could be the modification induced by ionizing irradiation? Is it so harsh as everybody believes? Does it lead to this kind of very harsh treatment at the end? That's the question mark. And what could be the extent of this modification? Okay, so if we look definitively, cannot see, but if we look at the polymers, what could be the impact at the polymer? And we check if the kind of cross-linking, so is a kind of cross-linking, as you can see on the top, that means that at the end our material will become stiffer, more rigid, but more rigid, maybe more fragile when there is a kind of solicitation. That's the drawback. That's the other side of the coin at the end. In the other side, if there is a scission, that means that we will cut everything, all the long chain in small pieces of chain. That means in that case, the total strength will be lower, but the flexibility will be higher. So don't believe it is exactly that. I strongly exaggerated on purpose the number of throttling or the number of scission which could happen into the polymer. I strongly generated that. So the question mark is, do we know the extent? Are we able indirectly to measure what could be the extent of all this modification? Okay, if we, for instance, we take a simple bag made of the SAT film, one of the purpose, of course, is to carry out. So that means directly, here you need to be robust, you need to get the perfect strength to be able to withstand, of course, the volume inside and the handling. We just ask that, nothing else. So to be able to do so, we check what could be the stencil strength. So once again, I will not describe into all the detail, but we are able to describe where the flexibility of the material is, where the rigidity is, what could be the total strength of the polymer by using tensile strength curve like that. And we can see once again there is a very good overlapping between the gamma, the X-ray, the beam, and even the non-sterile at the end. So at the end, up to 50 kg. We have many other examples up to 250 kg, but here I just stick to 50 kg when we can see there is no impact at all on the thermal property, no impact of the barrier property, no impact on the stencil strength. That means that the extent of all the structural modification we can say on the cross-linking is that weak at the end. Once again, I strongly invite you to read the numerous papers we have on that field if you would like to dive in. Okay, if we take another property we like, of course, about the film is to be able to store appropriately without any leak. And if we look at this just simple, I would say, application, you need to store to use in the trolley. And of course, as soon as you make this trolley move, it will create some vibrations. So that they have to withstand some vibration. They have to withstand as well tensile strength and vibration at the same time. To be able to understand how we can deal with that and how we can reach that property, we have performed some DMA, dynamic mechanical analysis. That means that at the same time we used a vibration of typically 1 Hertz, we heated up the sample to be sure that at the end we can get the viscoelastic property of our material. Once again, I won't describe everything, but it is clear you can see once again on overlapping about all the different curves after the X-ray, gamma, and E-beam irradiation at 50 kg once again. That means that all the thermal properties of our film is not impacted at 50 kg, whatever the radiation technology. That means as well the flexibility is kept up to 50 kg with whatever the radiation technology. That means at the end, the cross-linked event occurring in that kind of polymer, of course, with the additive package, with the antioxidant package, is weak because the additive package kept everything inside controlled. That is the key. Because we have selected a polyethylene adapted for the radiation. Okay. I have a video, I don't know if it works. It seems to work, yes. So I showed you directly, I would say, at the component level, the material construction level, and now, of course, we have something we cannot capture at all in the lab. We need to do some testing, to need to check what could be the synergy with different components, and to be sure that at the end, when the integrity of the connection and so forth, it is the same, once again, after the radiation, using either X-ray or gamma. So it is what we have done so far in the video, and we can see that when we fill up some bags at the nominal volume and for 24 hours, that there is no loss of the functionality, hopefully you will see, but that's the purpose we check, and no loss of the different sensor and so forth. And of course, we can reach the expected performance. Okay. Now, I showed you many, I would say, mechanical application, modification. For your interest today, I guess I need to focus a little bit more on the extractable world. So, as I said, many times the interaction of gamma rays and X-ray are the same, whatever finally the radiation source. So, definitively, we could expect that at the end, as soon as the modification, the interaction with the same, we saw that the nature of the radical as a seed of modification would be the same. Can we expect to get the same mechanisms of degradation? Is it something we can expect? So we found, when we started the journey as well, of course, with Armin and I, maybe a couple of articles in that field, not that much. But he said, yes, this is something we could expect. But this is something we wanted to check, of course. And of course, we expected to get exactly the same chemical compatibility. So what we have done so far is to compare, and it is also quite small, but in also a peer-reviewed paper. And we have also another Nature paper on that field to be sure what are the different extractable profile you can expect using different irradiation technologies. So what you can see, that is a perfect match. First of all, from a qualitative point of view regarding the number of extractable, we could be detected either with X-ray or gamma. So that means that the mechanisms of degradation is exactly the same, whatever the radiation source. That means also that the extractable profile is determined by the polymer you use and determined by the additive package you will be using, which is inside your polymer. So don't expect to see an infinite number of extractable profile because we don't have a numerous number of different polymers and we don't have so many antioxidants to be used in our pharma industry. For instance, if you take into account the EP 3.13X Simon mentioned about, it is described maybe 15 additives, not that much, and it is more or less always the same. So that means that we can expect to see more or less exactly the same degradation pathway for all our antioxidants, leading exactly to the same extractable profile, leading to the same byproduct. For my mind, you don't need to repeat forever the extractable testing. As soon as you have one big picture of the mechanism, you could understand that at the antioxidant level. And of course, you can see there are some polymer degradation product over there. Okay. So main takeaways, messages from my side. Yes, we could achieve the sterility by using either gamma or X-ray or even E-beam. Sometimes, of course, to be able to submit your product to the gamma X-ray radiation, you need to make an appropriate selection of material without any EL testing at the end. We are able also to monitor, to track what could be the seed of modification, the radical, and to be sure that at the end we can understand their fate, their history. What we saw that the nature is the same, whatever the radiation technology. The concentration will completely be dependent on the dose. That's normal. But and at the end, it gives a strong idea, a strong event that the interaction between the gamma, X-ray, E-beam with the matter is the same. And at the end, it leads to the same cascade of reaction inside the matter. And with the holistic approach which has been defined by the Team Nablo and by the BPAC as well, we are able to capture all the modifications. Thanks.